Welcome. Nilpotent groups have special roles in mathematics. They are a generalization of abelian groups. And as in abelian groups, balls in nilpotent groups grow no more than polynomially with the radius. And in some sense, this polynomial growth characterizes nilpotent groups. In the geometric viewpoint I will have in this series of videos, nilpotency will appear as a consequence of the presence of dilations. And in fact, tangents to Carnot-Karateodori spaces are very special nilpotent groups, which are called Carnot groups. Today, I will revise the notion of nilpotency for groups, Lie algebras, and linear transformations. Let's start. The term nilpotent is used in many situations in mathematics, okay? And maybe a student might be confused on the relation between these terms. So I will quickly review various notions of nilpotency and relate them. Okay, so this is so the definition of nilpotency can be given for groups, for Lie algebras, and for matrices. And so if you have a GLE group, or yeah, just a group, if you have G Lie algebra, and M linear transformation on a vector space, a linear map, linear transformation, then all these three objects can be said to be nilpotent if some condition is satisfied. Now, I would like to tell you what are these conditions. Okay, so let's start with the group. So G is a group. Then let's say that you have two subsets of the group. Subsets. And then you define the group generated by the commutators. So A bracket B denotes the subgroup of G, generated by the set of all the commutators between elements, one in A, the second one in B, where the commutator between two elements is A, B, A minus 1, B minus 1. This is called commutator, the commutator. Between A and B. Okay, so the set of commutators of A and B defines a subgroup, and this is how we denote it in this way. Now, then we consider this sequence. So we set G with index 1 to be just the group G itself. And then iteratively, we defined the I plus 1 element of the series to be the commutator between the ith element and the group G. So then we get a sequence. So the sequence Gi I from 1 to infinity is called lower central series. Or also descending central series. And a group, the group G, and G is said to be nilpotent of nilpotency step, or just step nilpotency step, let's give the name S, with S an integer. If the S element of the series is equal to the trivial group 1. So in other words, then, and of course, for all index greater than S, this is still going to be equal to 1. Now, to remember this, let me check if it is S or S plus 1, just the terminology, because what we want is that an abelian group will be the same of nilpotency step equal to 1. Okay, so we don't want S, but here we want S plus 1. Because for the abelian, of course, we have G1, it's just G, and as soon as you do the bracket between G and G, you just have the commutator, the identity, because all the elements commute. Okay, so from any index greater than 1, then you will have the trivial group. Okay, so this is what is a nilpotent group.
Of course, what I wrote is the definition of having nilpotency step less or equal than S. To really define step equal to S, one should require that all the previous elements in the lower central series are different than the trivial group.
Let's discuss about the algebras, okay? So let G be a Lie algebra. And then now we have for subsets A and B in G, we just subsets. We let AB to be the vector space subspace of G, vector subspace of G generated or spanned by the commutators, the set of commutators. A is in A, B is in B, where the bracket now is really the Lie bracket, where this bracket is the Lie bracket of G. Okay, and similar as for group, we set G1 to be G, and iteratively Gi plus 1 is Gi bracket with G, and then the sequence Gi I from 1 to infinity is called lower central series or descending central series, and G is said to be nilpotent of nilpotency step S, with S an integer, if G with power S plus 1 is equal to the trivial subalgebra, namely just the 0.
And as before for the case of groups, we ask that the previous elements of the lower central series are not trivial.
Okay. A comment about this lower central series is that so if A and B inside G are not just subsets but are subalgebras, like in the case where we perform the bracket with G with itself, then AB inside G is also subalgebra. And therefore, all these subsets GIs are subalgebras of G. Actually, something even stronger is true, and actually they are ideals, namely GI bracket with G is a subset of GI. So they're closed. They're not only closed under multiplications between the bracket between elements in GI, but also with bracket with an arbitrary element of G. And similarly, this the subgroup GI of a group, these are always normal subgroups. Okay, this was a side remark, algebraic side remark. Now let's go to transformations, linear transformations. So let's say we have V, a vector space, and we have M, an element in GLV. I recall this is just notation to say that this is a linear transformation of V, so linear map from V to V. Then by definition, M is nilpotent. So every element, so the element M is nilpotent of nilpotency. Is not now use the term index. You can put an index, just index S with S in N. If the power, the S power of S of M is equal to 0. Okay. And the example that you should have in mind is something like a matrix of this form. This is a 2 by 2 matrix. Now, if I take the square, this is pretty easy to check that this is 0. And in general, whenever you have an upper triangular matrix, if you take enough powers, then you have the 0 matrix. So let's keep this in mind, because these are the classical example of linear transformations that are nilpotent. Okay, let's see some examples of nilpotent groups, nilpotent Lie algebra, and more generally nilpotent transformations. So first example, so I will use actually in all the video this symbol n with the capital N with index small n. These are the nilpotent matrices. So these are the group of upper triangular matrices. So these are the matrices that have 1 in the diagonal, something above the diagonal, and 0 below. So these are matrices in G in the group of GLN. This group, one can prove that is a Nilpotent Lie group. Actually, topologically, this space is contractible. So let me just, this is contractible, in particular simply connected, contractible Nilpotent Lie group. The second example is for a Lie algebra, and let's take the Lie algebra of the above group. Okay, these are the matrices that have 0 in the diagonal, 0 below the diagonal, and something on above the diagonal. Okay, so these are just n by n matrices. This is a nilpotent Lie algebra. And moreover, each element of this Lie algebra is a nilpotent transformation. So this is a set made of nilpotent transformations. And again, the thing that you have to notice is that if you take, now let's make the example of a bigger matrix. If you take the square, what happens is the second diagonal is also going to be 0. Okay, and now you understand that. So now, if you iterate this, if you take k, the kth power, then you will have going to have the first k diagonals that are all 0. Therefore, eventually, all of the elements in here are going to be 0. Let me clarify the fact that you can have nilpotent Lie algebras that are not made by nilpotent transformations. Okay, so this example here is if you take the diagonal matrices, diagonal matrices, n by n matrix. So this is just, I'm saying, just you have something in the diagonal and 0 up and below. Okay, it's the element of GLN. Now this is actually an abelian Lie algebra. It's an abelian, and therefore nilpotent. Lie algebra, but there are no nilpotent transformations except the 0 matrix. So this is not made of nilpotent matrices. Okay. Okay. Now let's try to let's discuss how these 3 definitions are related. Okay. What I'm saying is not easy to prove. They're not obvious facts. You can try to prove them yourself, but there might be some hard exercise, but they're true. So that's and they clarify that there is a reason why we are just calling all these objects nilpotent. Okay, so let me just announce them as facts. They're good to know. You can ask me for references. Okay, first, for connected Lie group G, then it's equivalent to say that G is nilpotent as group, and its Lie algebra as Lie algebra is nilpotent. Okay, So for connected Lie groups is the same, requiring they are nilpotent or their Lie algebra is nilpotent. Okay. Second fact that goes as is called Engel's theorem. Suppose you have a finite dimensional Lie algebra. Then the Lie algebra G is nilpotent if and only if, for all elements of the Lie algebra, the adjoint map, which remember, this can be seen as a map from GL of G on GL of G, so a map from G to G linear. This transformation is nilpotent. Okay, so this is a theorem. I want you to notice something, that a priori, when you have this in this direction here, then a priori in the assumption, we have that for all x, there exists a k which might depend on x, such that the adjoint, the kth power of the adjoint of x, this is the zero matrix. But a posteriori, namely after one proved this theorem and therefore the matrix G is nilpotent, then we really know that there exists a uniform K. So there is a K for which all the adjoint, the kth power of the adjoints are zero for the matrix. Okay? So this is known as Engel theorem. Right? So it tells us a first relation between nilpotent Lie algebras and the nilpotency of some particular maps connected with the Lie algebra. But probably the most important theorem, the connecting these notions of nilpotency, is Birkhoff theorem. Birkhoff theorem. They said that whenever you have a nilpotent Lie algebra, then you can always see it as a subalgebra of this standard nilpotent Lie algebras we saw. This is Lie algebra of the group n sub n. So there exists some n, and there exists a map from G into the Lie algebra of nn. So recall that these are the strictly upper triangular matrices. This is a linear injective Lie algebra homomorphism. So it's an injective Lie algebra homomorphism. So in other words, really, like this algebra can be identified with a subalgebra of this nilpotent subalgebra. As a consequence, one has that whenever we have a simply connected nilpotent Lie group, then there exists some n, and there exists a Lie group embedding in an n, injective Lie group homomorphism. So Birkhoff's theorem, in other words, says that if you want to study simply connected Lie groups, it's enough to study subgroups of this nilpotent linear subgroup. At some point, we need to focus on Lie groups that admit dilations, and therefore topologically they are contractible. In particular, they are simply connected. So let's therefore focus now on simply connected nilpotent Lie groups, on which we have many properties. So recall first one thing from general Lie group theory, that there exists a one-to-one correspondence between simply connected Lie groups and Lie algebras. Okay. So, in other words, let's focus on simply connected on nilpotent Lie algebras. Okay. So for nilpotent Lie algebras, one can actually choose. Now we are going to explain why we can choose as a manifold Rn, but equipped with some product that written via a polynomial law. No. And this actually can be computed given by the Bacon-Campbell-Hausdorff formula. Okay, so I will try to explain more about this statement. Okay, so the main point is that for simply connected nilpotent groups, the exponential map is a global diffeomorphism, and really the Bacon-Campbell-Hausdorff formula is not a formula that only holds in the neighborhood of the identity, but really globally. Okay, let's state this as a theorem and then prove it. So theorem. So let's say that G is a simply connected Lie group. Then, first fact is the exponential map from the Lie algebra of G into G is a global diffeo. Remember, we already know that it's a diffeo between a neighborhood of 0 and a neighborhood of the identity. But in general, for arbitrary Lie groups, the exponential map may not be surjective, might not even be injective. Instead, here this will really be a global diffeomorphism. Second fact, the Bacon-Campbell-Hausdorff formula holds globally. Remember, we have this assumption simply connected, and I forgot to write nilpotent, right? Otherwise it's not true. So nilpotent. Okay, it's important. Okay. So it's true in general, but I will only give the proof for Lie groups that are a subgroup of the group of nilpotent matrices. By Birkhoff theorem, this covers the general case, but we haven't proved Birkhoff's theorem. So let's just give the proof for groups of nilpotent matrices. Namely, let's assume that there exists some n such that G is a subgroup of the n by n after triangular matrices with one in the diagonal. Therefore, okay, so hence what we have that maybe this, and let's fix it because this is actually the step. We're going to call it S. What we have is that if I take the S power of elements in the Lie algebra of G, then the S power is 0. And instead, if I take an element, let's call it B, in the group, I see it as a matrix, then if I remove the diagonal, which is the identity, then this is an nilpotent transformation. Okay, so we're going to use these facts. Okay, now let's remember the exponential map for matrices. So the exponential of a matrix A, now by definition, but then we also understood that this is the exponential of the Lie algebra, is the series of a to the k divided by k factorial, and k goes from 0 to infinity. But as we said, we are in the space of nilpotent matrices, so as soon as k is larger than s, this is going to be 0. So this is the same as saying of writing k from 0 to s, ak over k factorial. What we understand is that therefore this map A goes to AX is a polynomial map. So we get that exp from the Lie algebra of our group G into G, this is a polynomial map. This polynomial. Now, for matrices, we have a way of writing the inverse of the exponential, which we call logarithm, and we have again a series that in arbitrary linear groups only converge in a neighborhood of 0, or of the sorry, in the neighborhood of the identity of the group. So also the logarithm. So we have the formula log of b. Now we have to think of b of something that's a priori is close to the identity matrix, is the series k from 0 to infinity of, what was the formula? Was minus 1 to the k plus 1 divided by k that multiplies b minus the identity matrix to the power of k. So this is the general formula. Again, this matrix, in our case of nilpotent group, is a nilpotent transformation. So as soon as k is larger than s, this is 0. So the series is the same of writing from k to s, before s, of the same thing, k plus 1 divided by k, b minus I. Okay. Again, this is a polynomial, it's a polynomial map, and therefore converges for every value of b. So it's a global map. And these two polynomials, we know that they are inverse of each other in a neighborhood of the identity, right? But if you compose two polynomials, and you know that on an open set, they're 0, they're 0 everywhere, okay? Therefore, they are global inverse of each other. Just write is a polynomial map, and a local and global inverse of exp, because it is they're polynomials. Okay, so in particular, exp is a global diffeomorphism. Let's now consider the Becken-Campbell-Hausdorff formula. Moreover, so Becken-Campbell-Hausdorff formula tells us that we can write the logarithm of exp of x times exp of y. When x and y are close enough to the origin, they can be written as a sum of commutators of x and y. But in our case, x is a polynomial, log is a polynomial. Now, we have that this is a polynomial that in a neighborhood of 0 coincide with the, let me write polynomial formula by Becken-Campbell-Hausdorff. Let's remember the formula. The formula was something like, I hope I get the indexes correct. So it was n greater than 0, and then was minus 1 n plus 1 divided by n. Then there was double indices li plus si greater or equal than 0. And each of them is greater no, or should I write? Wait a second. This is okay. I was from 1 to n, and then we have the adjoint of x at 1 times, adjoint of 1 of y s 1 times, compose, add x r n times, add y s n minus 1, apply to y. This is divided by r factorial, s factorial, and then was the norm of s plus r. Okay, let's not forget, I might have done some mistakes in the indices, but what's important is that there exists this formula. So right, this formula, now we have polynomial matrices, and therefore as soon as the indices are too large, then this is going to be 0. So this formula is a finite sum in the case of abelian Lie groups. Right? Let's remember maybe the other way of writing for linear groups. The formula was this one, n plus 1 divided by n, and then there were just the products of the matrices, p1, y, q1, dot, 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 x, pn, y, qn, divided by p factorial and q factorial. Okay, and again, this was pi plus qi greater or equal than 0, and or strictly greater than 0. Okay, so some indices. Okay, again, when you multiply, when the sum of these indices is greater than s, then this is formula is 0. Okay, and again, so this polynomial therefore coincide with this other polynomial in a neighborhood of 0. This is what Becken-Campbell-Hausdorff formula says for arbitrary Lie groups. But now these are polynomial, and therefore they are equal everywhere. Okay? And this concludes the formula, the proof of the theorem. Now, let's see some consequences. A consequence, so consequences of x being a global diffeom. So the first consequence is that if G now is a simply connected Lie group, nilpotent Lie group, then for every, and let's take H to be a subalgebra of Lie, subalgebra. Then the image by exp of H, this is a simply connected closed subgroup of G. Remember, in general, we know that there exists, if G is not nilpotent, we know that there exists a subgroup with H as subalgebra. And this is the group generated by exp H. But now exp is surjective. Right? So this has to be the whole group. In particular, this is interesting because you can also apply this. Once we know that X is a global diffeomorphism, we know that if a priori we only know that G is simply connected, but now we know that it's diffeomorphic to Rn. So maybe this was a previous consequence. So G simply connected nilpotent, then this implies G homeomorphic to Rn, and therefore in particular is contractible. Okay. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.